Hi, welcome back. Today we're going to talk about power management, which is really about bringing together some of the things we've already talked about this term to operate the aircraft engine on a day-to-day basis. Power management is about selecting a power setting that's going to give you a desired performance for the phase of flight that you're in. Uh, it's important also, though, to balance that against the limitations of the engine so that we get a long life out of the engine. And your reference for that is always going to be the Pilot Operating Handbook. As you select a power setting, you have to take into account how much horsepower is required, the combustion pressures and temperatures, and I'm talking about specifically the temperature of the burning gases inside the combustion chamber here, because we don't want to lead to detonation or at the other extreme, spark plug fouling. We need to also take into account the engine temperatures, the cylinder head temperature and oil temperature, outside air temperature, ambient pressure, altitude effect, which we'll talk about more here in a few minutes, and other environmental factors. So just to review here, given a well-adjusted mixture, so let's leave mixture out of the equation for a moment, the more fuel we burn in the engine, the more heat we get, and therefore the more power we get out of the engine. We can burn more by either increasing the manifold pressure, or we can burn more by increasing the RPM. Remember back to our formula here, brake horsepower equals 2 pi times torque times RPM divided by 33,000, or we can rewrite that using a constant to simply say the shaft horsepower equals the constant times the torque times the RPM. It's torque and RPM that are always going to govern this, and we control torque through manifold pressure. The more fuel-air mixture that we allow into the cylinder on the intake stroke, the more pressure we're going to get here on the power stroke, and that's what gives us our torque, is the amount of pressure pushing down on this piston and therefore being applied to the crankshaft. So here's a chart from a typical 230 horsepower horizontally opposed six-cylinder. So this would probably be a Continental 0470, and it gives us horsepower based on manifold pressure and RPM. So if we set our torque here, in the example I'm giving here, 22 inches of manifold pressure, and we set the propeller control to govern the engine at 2200 RPM, then we're going to get 61% power, which is 140 brake horsepower. We can get more horsepower by changing just the RPM. So if we use the propeller control to increase the governed RPM to 2400, we have a power increase up to 70% brake horsepower. Going back to our previous setting of 22 inches of manifold pressure and 2200 RPM, we can also get that brake horsepower increase by keeping the RPM at 2200 but increasing the manifold pressure to 24 inches. So you can see we have a choice as a pilot. And assuming that this whole chart was in a pilot operating handbook, any of these combinations is fair game for us. So which one do we choose? Well, we choose the one that is going to give us a reasonably quiet cockpit for one thing. If we run it at 2600, it's probably going to be louder. If we run it at too low of an RPM in some aircraft, that causes some big vibrations, and we don't like that. So we're going to find an RPM that works for us and gives us a comfortable ride, and then an appropriate amount of manifold pressure to go with that. But we also take into account that the lower the RPM, the more manifold pressure we're going to have to use. And the more manifold pressure you use, the more likely it is that you're going to get detonation, because that's going to drive the temperature and the pressure inside the combustion chamber higher. So higher manifold pressure equals higher combustion chamber pressures, and that could lead to detonation. So it's going to be a trade-off, and it's going to vary from one aircraft to another. The bottom line is any of these combinations is fair game if they are in your pilot operating handbook as an approved power setting. Now with a fixed pitch propeller, we control manifold pressure and RPM at the same time, and all we have to reference is the tachometer, which shows RPM. The higher we set the manifold pressure, which we can't see, the higher the RPM is going to give us. So a given throttle setting will give us a different RPM depending on what the situation is. So it's a good indication of the power being produced, but you have to interpret it with other things. It's more true to say that the RPM for a fixed pitch propeller is a balance between how much torque is being applied by use of the throttle versus the drag on the propeller. The more drag there is, the more torque that is required in order to get a certain RPM. So in order for all of this to make sense, you're going to have to come up with some power settings for your particular aircraft. This chart is out of the Instrument Flight Training Manual by Peter Dogan. A really great book. I'm not sure if it's in print anymore. But it boiled instrument flying down into this basic concept of pitch plus power equals performance. And he had a half a dozen standard configurations that kind of summed up everything you would need to do on an instrument flight. So we have climb, cruise, cruise descent, so coming down off your cruising altitude at a higher airspeed, approach, which is typically 90 knots in a small aircraft, approach descent, which is at that same airspeed, and at a descent rate that's going to keep you on the glide slope, and then non-precision descent, which is a step down, which typically we want a higher rate of descent if we're doing non-precision approaches and doing step downs between fixes. And for each one of those, there was a manifold pressure and an RPM that would give you a certain power, and that in combination with a pitch attitude setting will give you a certain airspeed and vertical speed performance. And when we say pitch here, we're not talking about propeller pitch, we're talking about pitch attitude of the aircraft. How far above the horizon is the nose pointing? So a given power plus pitch is going to give you an airspeed and a VSI. And if you figure out what these are for your particular aircraft, they're going to be pretty close to the same from one day to the next. So in a fixed pitch airplane, if you're flying 172s around on instruments, you don't have to worry about manifold pressure if you're at the airspeed that you're targeting. But that's an important if. If you're targeting 90 knots, then you can't set the RPM while you're still at 80 knots, or it's going to mess everything up. So everything kind of has to match here. Now you can apply this technique to VFR flying as well, and I did that with my students when I was doing primary instruction. I would have them fill out this chart for the 152 or 172, whatever they were learning in, and come up with a configuration for VX climb, VY climb, cruise, normal descent, and there were a couple of other ones that we would put in there. Quite often I would have them figure one out for 90 knots, or 70 knots rather, level, and that would be our downwind configuration. So when we were working the pattern, there's no reason to go clear up to a cruise airspeed in the pattern, so we came up with a more sane pattern speed, and you can use the other blanks there for whatever you want. But the important thing is you have a starting place every day. And for pitch setting, rather than using a degrees above and below horizon, I prefer, if you're flying VFR, you should be looking out the window. So I'd have them draw a little picture here of how far above the horizon is the nose, or how far below the horizon is the nose when you're looking out the window. Here's an example that I found in one of my pilot operating handbooks for a Cessna 182. A student of mine had just purchased a 182 and wanted to check out, and so we went out, and the first thing we did, he was an instrument pilot, so the first thing we did is we went out and determined the power settings for all of the different configurations that we might need. And because it's a little bit higher performance airplane, we needed more configurations because sometimes we were flying without flaps at approach level. Sometimes we would have flaps in there, so there were various circumstances that we had to allow for. But this was a really handy, I wrote it right into a blank part of a page in the pilot operating handbook so that the next time I jumped in this airplane or one just like it, I would have a starting place and I could just refresh my memory and go from there. When you're at altitude, we are used to thinking in terms of altitude having a negative impact on engine performance. And that is true for if you're thinking in terms of the maximum power that the engine will produce. But for a specific brake horsepower setting, so for instance a cruise, you actually need less manifold pressure to give you that same brake horsepower if you're at a higher altitude. And there are a couple of reasons for this. One is that on the exhaust stroke, as the piston moves up and pushes the exhaust overboard, if it's lower pressure outside, it's easier for that piston to push the exhaust overboard. And so each of the cylinders, when they're on their exhaust stroke, is soaking up less of the energy that the engine is producing. An even bigger reason is that we've talked about the fact that the pressure in the combustion chamber is what is giving us our torque. And that is true. But if you zoom in and take just a little bit closer look at it, what we're really saying is that the difference in pressure between the top of the piston and the bottom of the piston is what's giving us our torque. And if the pressure inside the crankcase, which is atmospheric pressure, is lower because we're at a higher altitude, and we have the same pressure inside the combustion chamber, then we end up with more pressure on the piston and therefore more torque at the same manifold pressure. And so to get the same amount of torque, we actually need to adjust the manifold pressure down slightly when we're at higher altitudes for the same power setting. And you will find that reflected in the power settings in the pilot operating handbook for your aircraft. We'll take a closer look at that in class. So, less manifold pressure is required to produce a specific RPM at higher altitudes because of those two factors, but much less manifold pressure is available up there as well, unless you have a turbocharged engine. So, therefore, the maximum brake horsepower that you can get out of the engine is less at higher altitudes. So, selecting a power setting. How fast do we want to go, or how fast do we want to climb? How much fuel are we willing to burn? How high will we be? All of these things kind of determine what power setting we're going to select. Typical settings that we use on every flight. Takeoff is 100% of whatever we can get at the altitude that we're at. And that is referred to as the maximum rated power. It's limited by altitude at full throttle. It oftentimes carries a 5-minute limit, and it is often represented by the red line on various instruments. It is sometimes referred to as takeoff go-around power or toga power. Once we get off the ground, we don't need all that power, and there's a 5-minute limit on it anyway in some aircraft. And so we oftentimes reduce the power to 75%, which is typically the maximum continuous power that the aircraft is rated for. And so a 75% or less, what they're telling you is you can do that all day and not hurt the engine. And that's typically represented as the top of the green arc for both manifold pressure and RPM. If you have both of those gauges set at the top of the green, that's going to give you 75%. Once you get up into a cruise, then you have a bunch of choices open to you. You can push it hard and get up there at 65, 75%. Some books will let you get even up to 78-ish or so. But usually 75 is about as hard as you want to push it. The that would be considered a fast cruise. Normally we cruise around 65%. That's a real typical cruise. If you're trying to save on gas, if you're buying gas, then economy cruise is great. So 55% is a really nice setting. It'll give you fairly good economy, but still have most of your speed. Best range is way down around 40 and 50, and best endurance even lower than that. And those are often not even specified in the POH. You're kind of working off the chart there. So you have to be a little bit careful. The engine could be running pretty cold, and there's the risk of fouling plugs and things like that if you get down there into the 30s and 40s on the power settings. So you have to be a little bit careful there. But it is kind of nice to know that if you start running out of gas and need to extend your range or your time in the air to its maximum. If you're in a fixed pitch airplane, the RPM indicates that is your power setting instrument. It is indirect, as we've already discussed, and it has to take into account altitude, outside air temperature, and also airspeed. The propeller drag and torque are what determine RPM. So torque, your manifold pressure, i.e. your throttle, is only one of the two factors. You have to take into account the other one as well. In addition to that, at higher altitude, the less dense air produces less drag on the propeller, and so it's easier to make it spin fast. And so at higher altitudes, to get the same amount of power, you actually have to run it at a higher RPM, because if you set it at the same RPM you use down low, you're at a lower manifold pressure than usual, and that gives you less power. We'll take a closer look at that here. So here's a Cessna 172, and I've indicated the power settings that give us 65% brake horsepower. And you'll note that that gives us about the same fuel consumption regardless of our altitude here. It only varies by a tenth of a gallon per hour or so, all the way across the board, maybe 2/10. And that's practically nothing. And that is because it takes a certain amount of fuel to give you a given amount of power, and that doesn't really vary with altitude. It takes a certain amount of fuel to produce each of your horsepower. That's that old specific fuel consumption thing. But in order to get that power, note that it requires a different RPM. The higher you go, the more RPM it takes to get that 65% horsepower. And as a reward, at the higher altitudes, we get a higher true airspeed for us as well. So here's a typical rule of thumb for you. The more powerful the aircraft is that you're flying, and therefore the faster you can climb, the more worthwhile it is to climb higher for your cruising altitudes. Not really a big payoff for it in a 152 or a 172, but you get into a 182 and even a reasonably short cross country, just 45 minutes or an hour, it's worth it to pop on up to 8,500 feet, 9,500 feet. You'll get a lot better economy that way. You'll get there faster for less fuel. Let's take a look at a constant speed aircraft as well. So this is 172 RG, not something we fly a lot around here, but it represents how we fly constant speed equipped aircraft pretty well. So after takeoff at 500 or 1,000 feet above ground level, we reduce to max continuous power, which is the climb power. And to do that, we reduce the manifold pressure to the top of the green and then the RPM to the top of the green. And then we lean when we're at an altitude where the pilot operating handbook says that that's appropriate. During the climb, once we've set that power, we're going to have to readjust the manifold pressure every 1,000 feet, because as we climb, there's less atmospheric pressure, and you'll look down and you'll notice that the manifold pressure gauge is all of a sudden a little bit lower than the top of the green. And you're going to have to readjust that, and typically we just kind of consider it worth doing about every 1,000 feet or so. You're welcome to do it every 500 feet if you want. It's just that we're usually busy enough it's not worth it. At some point where our throttle is going to be full throttle, and that's what's called critical altitude. That's where full throttle is required in order to get the manifold pressure that you desire. Um, and above that, we're just going to have to take what we get. Now, during all of this, the governor's going to take care of the RPM, so the good news is that you won't have to worry about adjusting the propeller. Once it's set, as you make their power reduction for climb, the governor will take care of it and it'll hold it right at the RPM that's specified. Um, do know that when you adjust the RPM, it has an effect on manifold pressure. The higher the RPM, the more intake fuel air mixture is being demanded by the engine, and that will draw the manifold pressure down. So if you increase RPM, you can expect a decrease in manifold pressure, and vice versa. If you decrease the RPM, the manifold pressure is going to creep up a little bit. And so as you make your power settings, it's important to sort of anticipate that. If you're setting the manifold pressure first on a power reduction, for instance, you know you're going to reduce your RPM in a second. You might as well set the manifold pressure just a little bit low, so when you reduce the RPM, the manifold pressure creeps up to where you want it. If you miss that, it's not a big deal. You can just readjust once the RPM is set. So critical altitude again is the maximum altitude for the desired manifold pressure. We can desire a lot of different manifold pressures, and therefore there are a lot of critical altitudes that are possible. Full throttle in a normally aspirated engine, or full power rather, in a normally aspirated engine is sea level is critical. Um, because anything above sea level, you're not going to get your maximum manifold pressure. But during the climb, you'll probably get up a few thousand feet before you hit that point. For cruise, you'll get up even higher. In some aircraft, once you reach certain altitudes, because they know you just can't get manifold pressure up there, they'll allow you to run the RPM a little bit higher than the green arc in order to get a reasonable amount of power out of the engine for the climb. But it doesn't hurt the engine because you're running at a higher RPM, but by then your manifold pressure is very low. Plan ahead on your cruise. This isn't something you want to be pulling the pilot operating handbook out of the back of the seat and looking up while you fly. This is something you want to think about beforehand and select your power setting and kind of write it down on the knee board so it's there handy for you on your way out. Here's the 172 cruise charts, and that aircraft has a separate cruise performance table for each 2,000 foot increment all the way up to about 12,000. I picked just a couple of pages here, 2,000 and 8,000. Once again, I've selected a bunch of power settings that will work to give us around 65% brake horsepower. So at 2,000 feet, we can use 2,500 RPM and 22 inches manifold pressure, or we can use 23 squared, or 2,323 inches, or we could use 2,224 inches. Any of those give us the same horsepower within a brake horsepower or two, and a very similar fuel consumption in each case. Then we jump over to the 8,000 one, and we have once again, different power settings. So if we look, for instance, at the 2,400 RPM settings, at 2,000 feet, it takes 23 inches of manifold pressure. At 8,000 feet, it takes 2,400 RPM and 21 inches of manifold pressure to get about the same power. And that is that altitude effect in action. So being at a higher altitude, it takes a little bit less manifold pressure to get the same power. Cooling, you have to consider how much power you're producing and then how the engine is being cooled. So as a rule, the more fuel we burn, the more heat we produce, and we can increase either manifold pressure or RPM to do that. You also affect the temperature by adjusting the mixture for peak EGT, which is called out in a lot of pilot operating handbooks. So you have to take into the account that as well. That's probably not as big of an effect as adjusting manifold pressure or RPM, but it still is significant. We also have to consider economy. Traditionally, in small aircraft, people just consider the cruise, but you need to look at the whole flight profile because it's really about how much fuel you're going to burn during, all the way from takeoff to landing. And for some aircraft, uh, how you climb and descend is going to have an impact. Um, a steep climb versus a cruise climb, for instance, or long, slow letdowns, or a steeper letdown right at the end. What's going to give you the best economy? And that's something you're going to have to figure out for each aircraft. Typically, though, if you're as long as you're within parameters on the engine, a steep climb and a slow letdown will typically give you the best economy. Um, Mixture setting is a compromise between economy of fuel and economy of maintenance for the engine. Pretty standard to go 25 to 50 degrees rich of peak EGT, which won't give you the best fuel economy. That'll typically be at 25 or 50 degrees on the lean side of peak. Um, and so your pilot operating handbook may suggest things that are more aggressive than your industry standard. So you're going to have to consult with the company that you're flying with. There's no leaning in helicopters because if you make a mistake and pull that knob out just a little too far, the engine's going to quit. And since the engine is decoupled from the rotor system, if the engine's turning slower, it'll just flat quit. It won't restart when you push the knob back in. And then you're going to be too busy doing an auto rotation to reach down to the key and try and start it again. So we don't touch that knob in the helicopter at all. Stay within operating limits is always important. And you should have some basic power settings memorized for the aircraft that if you're flying it on a regular basis. So here's some examples of some of the limitations in a Cessna 150. We have max engine speed, a static RPM, which is how we test the engine. So with the brakes locked on the ground, we go to full power, carb heat off, and we should get the RPM should fall within this range. That's a good one to know in case you want to run the engine up and check it. Max oil temperature, oil pressure range. Those are things that it's good to be familiar with because it's important to once in a while check the gauge to make sure you've got the right gauge in there. I have been victim to a couple of airplanes over the years that had the wrong gauge installed in them. Some owner had replaced it at some time or another and hadn't bothered to make the green and red lines in the right places. So take a look at that too and make sure that the instruments in the airplane match that page in the pilot operating handbook. Couple of old wives' tales about engine power management. One is that the most likely engine failure is at the first power reduction. That does not statistically hold true. Most likely engine failure is when you're at full power, and so the whole takeoff and initial climb out is a high risk area, but that power reduction doesn't actually hurt the engine. That is, however, a very likely time for your flight instructor to fail in the engine, and so I think that's how that rumor got started. And then the other wives' tale is that the RPMs in hundreds cannot be less than the manifold pressure in inches, and that's completely bogus. You open up the POH and there's all sorts of power settings where the RPMs in hundreds is less than the manifold pressure, and that's fine. But it comes from a well-intended place, though, and that is that people want to avoid detonation. And if you have low RPM and high manifold pressure, you are more likely to get detonation. But this rule is bogus because RPM is a speed and manifold pressure is a pressure, so they don't have anything to do with each other. Then real quick, I just want to talk about engine shutdown. There's a couple of things that you can do as part of the shutdown. One is to check the switch. This is something that the mechanic should be doing every 100 hours, but it's also really super easy to do, so a lot of companies will have you do this every time you shut down. And a off check is simply at an idle, momentarily to move the key to off and then back on again. And you don't stop and wait to see what's going to happen. You just go off and on that fast. And then you think, okay, did I hear the engine cut out? Because that's what should happen, is the engine should momentarily cut out when it's in the off position. And then you shut the engine down normally. Now, if it didn't cut out, it means one of the magnetos is hot. The P lead is not connected. So that is a squawk. You should squawk the aircraft, have a mechanic pull it off the flight line immediately, because it's a hazard sitting out there on the flight line in that condition, and they should track down the problem and fix that. Then when it comes time to shut the engine down, always refer to your POH for the procedure. But I've found that this mnemonic will work in a pinch in every aircraft that I've ever encountered. So you start with the radios. The avionics master is a fine way to turn those off, but you don't leave radios on while you're shutting the engine down, because you get voltage spikes as the alternator or generator come to a stop, and that can ruin the radios. Turn off the accessories, any lights that you don't want left on. Most schools are in the habit of leaving the beacon on, and that's so that people can tell from a distance whether you've left the master switch on or not, so you don't run the battery down. So you turn off any lights that you're not going to leave on. Then you go mixture idle cutoff, master switch off, mags. So radios, accessories, mixture, master, mags. If you can kind of memorize that little mnemonic, radios, accessories, mixture, master, mags, then you'll never forget to turn your mags off. You'll never forget to turn the master switch off, and you'll have everything pretty much covered. Now there's a little bit of disagreement as to what RPM to have this done at. If your POH doesn't specify, then there's a little bit of your choice here. I've done it at an idle, and that works fine on most Cessnas. You will get a cleaner shut-off if you bring the RPM up to about 1,000 RPM, because when you go to mixture idle cutoff, that means you're going to get a nice clean fuel-free charge of air up in through the cylinders, and that gets a nice clean shut-off and doesn't leave as much fuel sitting there in the cylinder. That's probably a little bit better. If you get the RPM too high, though, if you were to maybe go up to like 1,500 and shut it off, that could slam the dynamic dampers around a little bit if your engine is so equipped. So you want to be careful about that. I have encountered a couple of engines that require a higher RPM like that to shut down, but I wouldn't do that unless it's required by the POH. That's it, and we will see you in class to maybe talk about this some more and do a little bit of experimentation.